Here's a word problem that deals with quadratics, and it's quite practical, and it's a very good problem that has a lot you can learn from it. Okay, here's a situation. You've got all these rectangles here, and it says a high school wants to double the size of its existing parking lot by adding an expansion. Okay, here's the expanded lot in blue. Okay, it's going to be some strange L shape here with dimensions x and x on this dimension here. We don't know for sure the full dimension there or the full dimension there, but we can get this quite easily. Now, if they're going to double the lot, keep in mind that the blue area has got to be the same size as the existing parking lot, right? If you're doubling it, the old one's half the total, right? The total would be both these L shapes together, red and blue. So if the blue equals the red, they will have doubled it. Think about it. Let's just say the red was 5,000 square feet. If the blue area they're going to add was 5,000 square feet, then you'd have 10,000 total. You've doubled the red, which was 5,000. Okay, so first of all, the new area, the blue, is going to equal the old area, the red. So now let's set about finding the old area first of all. Okay, so let's first take a look. There's a number of ways to do this. This is the way I think is probably easiest to approach it. Look at the green rectangle. This thing's going to be 240 this dimension because that is 165 plus 75, and it's going to be 375 this way, 300 plus 75. Okay, so if I go 240 times 375, that's feet and that's feet, I'm going to get 90,000 square feet. Okay, that's big. Okay, now that's the area of the green. That's the school plus the old parking lot. If I subtract out the area of the school, then I will have the area of the existing parking lot. I'll call it AP for parking lot. That's the red area. Actually, maybe I'll write it in red. Maybe that makes sense. Okay, the red area will be area of the existing parking lot. Okay, area of the school is going to be this area here in black. Okay, and I know that area is going to be 300 times 165. So I subtract out the area of the school, right? The big green triangle minus the black, big green rectangle minus the black rectangle gives me the red rectangle. Or it's not really rectangle, but it's the leftover shape. Okay, so I hope you get that. Area of the school then, right? 165 by 300. If I take away this black rectangle here, I will have the red, right? So green minus black equals red. Okay, well, what's the black? 300 times 165. Let's do that. Okay, if you do the math there, okay, you will get, I believe, 49,500. Okay, so 90,000, right? The whole green area minus 49,500 should give me the red area, which is the existing parking lot. Okay, and if I do the math there, I think I get, oh, what do I get? 90,000 minus 49,500 equals 40,500. Okay, so 40,500 is the area of the existing parking lot, the red area, this L-shaped combination of rectangles. Okay, I hope you're with me so far. Okay, so now let's keep working. All right, so now remember what we said earlier. If we're going to double the size of the total parking area, the blue must equal the red. Okay, so now I can do a similar calculation here. I can figure out the shape of the blue. Okay, there's a number of ways to do this, but I still think these big rectangles will work. So let's try this. Okay, now I'm going to go in blue, and let's look at those dimensions here. Okay, we know this is 375 all the way from here to here. When I add x, that's going to be 375 plus x. Remember, that's what I'm trying to find. By how much should I expand this parking lot? Okay, now let's look at the height or the width, whatever you want to call it. I know from here to here is 240, it's 165 plus 75, oh, plus x. So the height is going to be 240 plus x. Oh, and you can see right now this is shaping up to be a quadratic. So that's the area of the big, full, gigantic rectangle. Okay, that's not the area of the blue. That's the shape of the whole biggest rectangle we have there. Now all I have to do is subtract out, well, that original rectangle, the 375 and the 240. 375 and 240. I already figured that. That's 90,000. So the big giant rectangle minus 90,000 is the area of the blue. Oh, and I know the area of the blue has to equal the area of the red, which we just found. It's 40,500. Okay, so it's a big long quadratic. It's spilled over onto two lines. Okay, but now I can see minus 90,000. Okay, and 40,500. If you just work through it and have faith, you'll see some nice things happen for you here. Okay, so first, we're used to the x's being first, but they're not. Okay, so let's just do our FOIL. First, 375 times 240. Let's see, what is that? 375. We already did it, but let's just be sure here. Okay, 375, 240 gives me 90,000 is one term of my polynomial. Okay, now I'm going to do this times this, and I'm going to get 375x. I'm going to go this times this. I'm going to get 240x. And I'm spilling onto another line again, but I'm going to have my x squared term. Okay, so I'm sorry it goes onto two lines, but it's still equal to 40,500, right? Because this was the area of the, oh, I lost something here, minus the 90,000. Don't forget that, minus 90,000, right? So this polynomial here was the big gigantic blue rectangle, the whole thing, right? Minus the green rectangle, 375 by 240, and that's the area of the blue. And I know the area of the blue has to be equal to the area of the red, the original red L shape, because it has to be equal. If they're going to double it, it has to be equal. So big, gigantic rectangle minus the 90,000 rectangle has to equal to 40,500. I hope you followed that this far. Now let's do the math. 90,000 minus 90,000, those go away. All I'm left with, and I'll move it to the front because we're comfortable with that, x squared, 375 and 240. I think that gives me 615x. And yes, go ahead and use a calculator. These two terms went away. They canceled. What's on the other side is 40,500. And now I'm going to get minus 40,500 when I bring it back to this side because I want to set everything equal to 0. Okay, so now what do we got? I've got a quadratic with one unknown. We could use the quadratic formula. That's going to be an awful lot of math. Why don't we do something differently? Take a good look at this. X squared, right? A is 1, B is plus 615, C is minus 40,500. Let's just remember this and just go to the internet. Guys, I did a quick Google search. I just typed it in, solutions for x squared. This is how computers see a exponent. That little caret sign, it's on your keyboard. It's the top of the 6 button. So I just typed in x, shift 6, it gives me that caret. That means x squared plus 615x minus 40,500. I just Googled it, solutions for this. Look what I came up with. Mathisfun.com. Mathisfun.com gives me a quadratic problem solver here. And so if you remember my problem here, let's go back. 1x squared plus 615x. So I'm just going to put in a 1x squared plus 615x. What was the number again? 40,500. 40,500. It was minus, so minus 40,500. And look at that. It kicks out two solutions. Minus 675 and 60. Notice it calls them roots, but that's what we learned. Those are the zeros of the function, or the zeros of the parabola. What this means is you have this gigantic parabola they've shown you here in red. This gigantic parabola crosses the x-axis in two places. When x equals minus 675 and when x equals 60. Okay, that's when the functions equal 0. Those are your solutions. And that's all you're doing is you're solving for x. So we said x equals 60 and x equals, what was it again? Minus 675. You guys, in our drawing, what is minus 675? First of all, that number is bigger than all the shapes in our entire drawing. It makes no sense at all. What's a negative x? You'd be getting smaller. We're not decreasing the parking lot. In quadratic equations, often you will get one negative answer that makes no sense, has no bearing on reality. Throw it out. Ignore it. 60 is the answer we want to look at. Is 60, does that make sense? Well, we said the blue has to be the same size as the red. The dimensions of the red were 75 feet here and 75 feet here. Could we get double the size if it was 60? Well, yeah, because the blue is longer than this portion on the red. Oh, and it's taller than the corresponding portion on the red. So it doesn't need to be 75. You'd be more than doubling it if x was 75. So 60 seems reasonable. 60 is the right answer. And I didn't even have to use quadratic formula because I have at my disposal here cool websites like mathisfun.com. I'm not sure what else Google would have given you here, but Google it. See what you get. Okay, if I did this, click on this one. Oh, this looks like some guy is doing the exact same problem we're doing here. Look at that. And what's he get? He got minus 615 somewhere. No, where did he get his answer? He got a 60 here, and he got some bogus answer later. He got minus 675 right there. Don't take this as the link. It can't be negative. He does the other work, and he gets it to 60, so x equals 60. Somebody else is doing the same problem you're doing. It's amazing what you can find on the internet. Okay, so our solution here is valid. They need to expand that parking lot by 60 feet on this side and 60 feet on this side, and now that L-shaped will be equal to the red L shape, and they will have doubled their parking lot just like it asks.